My name is Pascal Poupart. In this module, we're going to cover the basics of partially observable reinforcement learning. In particular, we're going to discuss one important algorithm, which is an extension of Q-learning to partially observable domains. I will first introduce partially observable Markov decision processes, also known as POMDPs, since these provide the foundations to reinforcement learning in partially observable domains. Now, POMDPs, at their core, they're based on hidden Markov models, so that's really the part that allows us to link observations to the states that are not directly observable. But in recent years, hidden Markov models have been generalized to now recurrent neural networks, and then so we're going to build on top of that, and in particular we're going to discuss an extension of DQNs that uses recurrent neural networks and is known as deep recurrent Q networks. As a quick recap, we've got here our usual picture for reinforcement learning. So in particular, we've got our agent that executes actions. These influence the environment, and then in return, the agent receives some rewards and some state information. Now, the difference in partially observable reinforcement learning is that we don't have access to the state, or at least it's not directly observable, and instead we have observations that are simply correlated with the underlying state. Now, the goal will be the same as before, so we're going to try to choose some actions that maximize the rewards, but the difference is that now those actions are going to be conditioned only on the observations and not the state. At the core of reinforcement learning, there is a sequence of states based on which the agent would normally take actions. Now, if you recall, this sequence of state follows a Markov process. So in other words, this is a stochastic process that is governed by some transition properties, and we typically make two assumptions. The first one is that the process is Markovian, and what this means is that to determine the probability of the current state, then instead of considering all the previous states, it is sufficient to consider only the immediately previous state. The second assumption is that the process is stationary, which means that it doesn't matter what time step we consider, the transition properties are going to be the same at every time step. In partially observable reinforcement learning, we don't have access to the states. So instead, we have access to some observations that are correlated with the states, and this means that really the Markov process for the states should really be considered as a hidden Markov model that includes a sequence of states but also observations. And the idea is that what's denoted here in red, the observations, they are observable, whereas what is in black, which are the underlying states, these are not observable, they're in fact hidden. So that's where the name hidden Markov model comes from. Now, in terms of specifying a hidden Markov model, we're now going to have two components. So we have, as usual, the components for the process, the state sequence, that's essentially the transition dynamics, but we also have an observation distribution that tells us with what probability we're going to make certain observations in each state. Hidden Markov models became really popular many years ago in the context of speech recognition. In fact, it was speech recognition that put them on the map. So here, the problem of speech recognition is a problem of recognizing what are the words that have been spoken based on some audio signal. And we can think of this audio signal as really being some waveform where there's some amplitude. We can also view it in the frequency domain. But the idea is that we're going to extract some features from that, and then we're going to discretize those features into frames at different time steps. And treat them as observations. So these frames of features are observations, and then based on those observations, we're going to try to recognize the word that corresponds to this audio signal. So for instance, if somebody says Bayes' theorem, then this could be the audio signal, and the hidden words which are Bayes and then theorem would correspond to the hidden states. So the problem of speech recognition is really the problem of computing the probability of different hidden states, here corresponding to words, based on all the past observations which correspond to the frames of this audio signal. The foundation of reinforcement learning is really Markov decision processes. So here, as a quick recap, we've got the influence diagram representation of a Markov decision process, and you can see that we have our usual Markov process. This is our sequence of states in the middle, the actions that are being selected or optimized based on those states, and then the corresponding rewards. When states are not directly observable, then the Markov decision process becomes a partially observable Markov decision process. The key here is to introduce some observations, and you'll notice that now actions are conditioned on the observations as opposed to the states, because the observations are what's observable, whereas the states are not. And in addition, you'll notice that we have many arrows. What they correspond to is the fact that an action later in time can be chosen based on all the previous observations, and that reflects the fact that if we only consider the very last observation, it might not contain all the information that could really help us optimize the choice of action. This last observation perhaps is just an incomplete or at best correlated version of the current state, but it does not contain all the information of that state. Instead, if we augment it with some of the previous observations, then we can get more information, and perhaps we can get a better choice of action. Now, as you can imagine though, the fact that we have so many arrows is going to make things intractable, and therefore there will be some computational issues. We can define formally a partially observable Markov decision process with the following components. Here you'll notice that I've highlighted in red what are the new components in comparison to a fully observable Markov decision process. So more precisely, we have observations, and we also have the observation model, which is our distribution over observations given the last state and action. If we're doing reinforcement learning, then on top of that, there are some components that are unknown. So really our model here is unknown, so that means we don't know what are the transition, observation, and reward models, and that's why I shaded those. If we're also doing partially observable reinforcement learning, then we don't get to observe the states, and that's why this is shaded. So really what's left to partially observable reinforcement learning corresponds just to the observations, the actions, and the rewards, and obviously we still have our discount factor in the horizon, and the problem remains the same. So we're going to optimize a policy that maximizes the sum of discounted expected rewards. A simple heuristic to tackle partially observable reinforcement learning consists of simply approximating the state that is unobservable by the last observation, or otherwise a finite window of previous observations. So for instance, if we look in this diagram, you see each action has a parent that corresponds just to the last observation, so that means that we're going to select the action based on the last observation only. So this is as if we were treating that last observation as a state, and then this is computation simple. In fact, this approach allows us to use any of the previous existing algorithms for fully observable reinforcement learning, but the drawback is that this last observation may not contain all the information of the underlying state. So if we were going to consider some of the previous observations too, and let's say that they provide additional information, then we could obtain better actions. So this approach is clearly going to be suboptimal in general, but it is computationally simple, and again, any existing reinforcement learning technique can be used. An alternative to selecting actions just based on the last observation or finite window of observation would be to do belief monitoring. So here belief monitoring exploits the fact that we have a hidden Markov model. So if you recall, our hidden Markov model has this graphical representation, and then in terms of quantification, we have an initial state distribution, we've got the transition probabilities, and also the observation probabilities. Now we can use those components to do belief monitoring, which really means computing a posterior distribution over the current state given the past observation. So intuitively, the idea here is that normally if we would like to do optimal decision making, we should consider all the past observations, but instead of really conditioning on all of those observations, why don't we compute some sufficient statistic that essentially corresponds to the same information as all those past observations? And the idea is that ideally, if we had access to the current state, then we would just select our action based on that. So really, those past observations, we can use them to try to infer a distribution over that current state. So we don't observe that current state, but we can estimate a distribution over that current state, and that's what belief monitoring is about. Now, the equation for belief monitoring is very simple. What it says is that the posterior over the current state can be computed by first multiplying our observation distribution, then we multiply the transition dynamics, and we multiply what is our previous beliefs, so that's our distribution over the previous state given the past observations. So the idea is that you see, we start by computing a distribution over the first state given the current observation. That gives us an initial belief. Then at the next time step, we'll compute the belief for S1 given O2 and O1, but that will depend on what was our belief of S0 given O1. That's what this equation shows, is that we can recursively compute a belief at each time step based on the belief at the previous time step using this equation. With the advent of neural networks, we can generalize this notion of belief monitoring based on hidden Markov models by using recurrent neural networks. So here the idea is that a recurrent neural network is really a neural network that has some outputs that will feed back into the network, therefore creating a recurrence. So here I've got a simple example. So there's some quantity x that feeds into h, but then h will feed back into itself. And the idea here is that this loop with this little black square indicates that this is a connection over time that creates a recurrence. So now if we unroll or if we unfold this network, then we would get the following representation, which actually resembles the one of a hidden Markov model. So here h corresponds to the hidden state of this neural network. The hidden state at each time step, you see, will influence the hidden state at the next time step. So this is similar to our state process in a hidden Markov model. And then we have some inputs. These are the x's. They correspond intuitively to observations, and then they will influence what is the hidden state. So the idea is that we have a function f that takes as input the previous hidden state as well as the current observation, and then we'll compute a new hidden state. So this is very similar to belief monitoring, where before we were computing a distribution over the states, given the distribution over the states at the previous time step, and given the observation at the current time step. So you see the process is really similar, and it turns out that we can think of a hidden Markov model as really just a special case of recurrent neural net, simply because recurrent neural networks could consider much more flexible types of updates that would be encoded here by f. So f doesn't have to be just the update that we've seen on the previous slide, but it could be all sorts of complicated and nonlinear updates that allow us to essentially compute some embedding of the information provided by the observations at each time step. So we're going to use that now to do some reinforcement learning. Recurrent neural networks can be trained in the same way as regular neural networks. The idea is that the recurrent neural network is going to be unrolled into a network of a fixed length, and then we're going to do backpropagation on that network. Because it's a network that's unrolled over time, then we call that backpropagation through time. The other aspect is that the network will have weights that are shared from one time step to the other. This really corresponds to the stationary assumption that we discussed for hidden Markov models. So those weights that are shared ensure that we compute the same thing at every time step. But then when we compute the gradient, what will happen is, because the weights are shared, we'll need to accumulate the gradients of all those weights into a single gradient. Finally, when we optimize recurrent neural networks, in practice, there are often some challenges. These consist of the gradient vanishing and otherwise explosion problem. So this arises because we have a network that is unrolled. So if we have gradients that are small at every time step and we kind of multiply them, then they will get smaller and smaller and vanish. But if they're also too large, they might get bigger and bigger and bigger and then explode. Another issue is that the network might have some trouble dealing with information that it needs to remember over a long range. So ideally, you see an observation at the beginning of the network would be captured into the hidden state and then propagated at every time step, so it becomes available at the end of the whole sequence. The trouble is that at every time step, the network might simply perturb the information in that hidden representation in a way where it will gradually forget what it has observed at the beginning, and therefore it will have difficulty with long-range memory. The last challenge that is common with recurrent neural network will be what is known as prediction drift. So the network makes some predictions at every time step, and now if it makes an error at a certain time step in terms of computing the hidden representation, well, that error will feed into the next time step, and then it will likely increase because it will make an error again. So errors accumulate over time, and then we have a drift in terms of the prediction. We can tackle those issues by considering a special class of recurrent neural networks that are known as long-term memory networks, or LSTM networks. These networks are special in the sense that they have a gated structure, and this gated structure will help to control memorization and also forgetting in recurrent neural networks. So this in turn will help to mitigate the gradient vanishing problem and also to facilitate long-term memory, or at least improve the length of the memory that the network can effectively work with. So concretely, our recurrent neural network takes as input some value. Then there's going to be an input gate, so that's going to be some value computed between 0 and 1, where if it is 0 and we multiply that by the input, then it will have the effect of simply dropping that input. And if we multiply by 1 instead, then it will be the same as if the gate was open and now the input will be allowed to flow through and be combined with the hidden state. Then the hidden state would normally get updated at every time step using the recurrence. And then in that recurrence, we're also going to introduce a gate. So that's going to be the forget gate. Again, it will have a value between 0 and 1. And when we multiply, you see the previous hidden state by this forget gate, it will determine whether we forget or allow the previous value to flow through and be combined for the computation of the hidden state at the next step. And then finally, when we want to make a prediction, then we're going to produce an output, and then we can regulate as well the information that comes from the hidden state into the output via an output gate that again has a value between 0 and 1. So here the idea is that these gates can help with the gradient vanishing problem simply because if we have, for instance, a forget gate that can mitigate or often, drop values, then it can prevent them from ever exploding, and then at the same time it can also help in terms of preventing them from becoming too small. So the gates here provide an explicit mechanism that the network can use to essentially regulate by itself the size of those gradients, especially gradient vanishing and gradient exploding. In the same way, the forget gate will also help to enable memory over a longer horizon. So if the forget gate is always open, so in the sense that it always allows the information to flow through, then there's a better chance that this information will be kept over a longer period of time, and that will allow longer memory. When we unroll an LSTM network, we can think of it as really just taking a regular recurrent neural network and then introducing some gates. So the idea is that for each connection, there's going to be a gate. So for instance, here we've got an input gate that will multiply the input to decide whether the input should be fed to the hidden state. And the input gate again is a value between 0 and 1, where 0 will have the effect of nullifying or dropping that input, and 1 will have the effect of passing it through. We also have some forget gates that decide what information is passed from one hidden state to the next, and then some output gates that will decide what information is passed as output based on the hidden state. So this explanation, in fact, is not the standard explanation for LSTMs, although there are several ways of defining LSTMs, and what I'm explaining here is just one very special view. It's not the standard view, but it is a simple and intuitive view that helps us understand, at least at a high level, how LSTMs actually work. One more thing to explain is that those gates, they're going to get information from somewhere, and the idea is that they will take as input what is the current input as well as the previous hidden state. So you see, the input gate, the forget gate, the output gate, all of them have as parents the current input as well as the previous hidden state. So that's the information that is used, and then those links indicate that now we have a function, a learnable function that's going to determine by computing, I guess, a value between 0 and 1, what are those gates, and then those gates then multiply the corresponding links. And this is what happens at every time step. We're now ready to combine everything that we've discussed into an algorithm known as deep recurrent Q network. This algorithm does partially observable reinforcement learning, and it was proposed in 2016 by Hosnecht and Stone. We have here a graphical representation of this algorithm, but the intuition is simply that the transition model is going to be encoded by an LSTM network, and then the observation model, we're simply going to use a convolutional neural network to process observations that really correspond to images. So when it was proposed, this was in the context of Atari games, so the observations were really screenshots of the game, so that means images, and therefore a convolutional neural net is well suited for that purpose. So we have an image here as input, it's processed by a convolutional neural net, it produces an embedding, and the intuition is that this embedding really can be combined with the previous hidden state by a recurrent neural net. In fact, in this case here, an LSTM network. So we've got here, you see this part is the LSTM network that computes recursively a hidden representation. And the idea is that you see the hidden representation at any given time step combines the current observation, so the last image, as well as the previous observations through the previous hidden states. Then once we have a hidden representation like this, then since we're doing reinforcement learning, our goal is going to be to predict some Q values. So you see, if we were doing Q learning, we would normally have a Q network that maps some state representation to some Q values. Now, since we do not observe the state directly, instead we have a hidden state representation that comes from our LSTM network, and then we the output, the prediction that's based on that, is now going to be given by the Q network. So this little part here is the Q network, and it simply produces Q values as output. So this is really an extension of the DQN algorithm. But instead of just having a Q network, we have a Q network that receives input from the predictions of an LSTM network, and then inside this LSTM network, if we have complex observations like images, then we can use a convolutional neural net as the observation model to process those observations. So that's the main idea. Coding a deep recurrent Q network is not very difficult. What we can do is simply modify the DQN algorithm based on a few things. Here I've got the pseudocode of DQN, and I've highlighted in red what are the changes that we need to make in order to get this deep recurrent Q network algorithm. The first modification is that we're going to add entire episodes to the experience buffer. So normally, if you recall, for DQN, we add tuples of a state, action, state, reward, but here we add an entire episode, and that's going to be necessary because we need to keep together the sequence of observations that, and this will be needed for the recurrent neural net down the road. Once we have episodes into our buffer, then we can sample an episode from the buffer and then start training based on that episode. Now, given an episode, what we'll do are some gradient computation to update our Q network and the recurrent neural network. The idea is that normally the Q network would take as input state action pairs, but now it will take as input the prediction of the recurrent neural net. In this case, that prediction will really just be this hidden state, and we can think of this hidden state as some sort of guess or approximation or belief about what the true underlying state might be. So that's the main difference. You see, so we're going to compose together a recurrent neural net with a Q network. So they get composed into one big function, really, that we differentiate through. But you see, the equation here is really the temporal difference times the derivative of this Q network applied to the output of the recurrent neural network. Here you see the weights of those two networks are simply denoted by W. So we're going to update the weights of those two networks simultaneously, and then it's just done as usual. So that's it. This is really just the DQN algorithm, but where states are replaced by a recurrent neural network. This slide provides some results that compare the DRQN, so Deep Recurrent Q Network, to regular DQN. Those results are taken from the paper by Hosnek and Stone on DRQN, and it was applied to some Atari games where we compare the rewards for DRQN to the rewards for regular DQN. Here they have two columns for DQN because there was the column of the original paper by Ni et al., but then they were not able to obtain the same results, so they also indicated what rewards they obtained with their implementation of DQN. So now when we compare this column to the previous one, we can see that for some games, if we make the assumption that the last observation is sufficient, which is what DQN does, then that assumption might not be realistic, and then there's a loss in decision quality. So you see there are some games like Frostbite where we can gain a lot by considering multiple past observations with a recurrent Q network. Now, to induce more partial observability, the authors did an additional experiment where here an observation would be made with a certain probability. So normally you get an observation at every time step, but if instead you get an observation only with some probability, so when this probability is low, there's going to be a lot of partial observability, and when this probability is high, that means we're going to observe the observations all the time or most of the time, and therefore we have more information. So we can see that DRQN tend to perform much better than DQN, especially in the case where there's a lot of partial observability. Okay, so this is it. Thank you, and I hope that this was helpful.